Okay, so now we know what's the basic E of Q model. Now let's extend the basic model to handle some more situations. First, we will talk about what will happen if we have ordering lead time. Okay, so after you make an order, your orders will go to your warehouse after a fixed period of time. Or we will talk about another thing. It's called economic production quantity. That means once you initiate a production process or you make your product instead of buying it from others. Once you make a production process, you will start to increase your inventory level gradually, but not immediately go to Q. Okay? Because your factory is producing product while you are using products. We're going to see how to do that. So suppose there is an ordering lead time, then that means after we place an order, we will receive the product after L year. And of course, L typically is a number less than 1. Okay? But we fix our unit of measure to be year. In this case, what we care about is a reorder point, okay? Something like this. Reorder point is an inventory level at which we should place an order. So let's see the graph. Suppose this is the inventory level, okay? According to a certain order quantity. Then given that, if we know after we place an order, we need L year to get our product, then we certainly know that we should have received the order exactly when we have no product. Okay, so it's at this time point we should get the supply. So pushing back for L years, we know this is the time we should place an order, and this is the reorder point. When we watch at warehouse, if we watch at our warehouse and see the inventory level is here, we should place an order. Then the order will get into our warehouse exactly when we have no inventory. Okay, so we want to solve for reorder points, and that's just a question about when to order. Immediately you can see whether you have this positive lead time does not affect your optimal quantity, right? You just need to switch your ordering time, but the ordering quantity will remain the same. So the question is just about reorder points. Suppose R is the reorder point. What we want is to calculate R according to other parameters and our optimal order quantity or order cycle time. Let's see the first case. Given our all the parameters, we know we can solve Q star. Okay, suppose this is Q star. Then we know that for each cycle there is a cycle time, and the T star is our optimal cycle time. If our L is less than or equal to a cycle time, well, just like this. Okay, suppose this is L. Then our R can be determined easily. We are asking how long this particular edge is, right? And the width is L, and the slope is capital D. So R must be L times D. Or you can think we need this amount of time, and D is the rate we consume products. So of course we need L times D. We need to order when we still have L times D, so that after L years we use all of them and we have no inventory. Another situation that may happen is L is so long and is greater than or equal to capital D. In this case, we certainly cannot use the original formula because that's going to give us an infeasible solution. Why? Suppose I'm looking at here. I want to get our product at this moment. Okay, if R is very long, like this, and sorry, this is L. If L is very long, then according to the old formula, we're going to have this as our reorder point. But of course, this is impossible. We will never see our inventory level be so high because each time we only replenish to this level. But our reorder point cannot be here, right? It will never be achieved and we will never replenish. So we must do some adjustments. Okay, so let me remove something here. Okay, so again, suppose this is our lead time. We know actually what we should do is to treat the other thing here as our true lead time, right? We should order exactly when we have this amount, and then inventory will deplete, and we will receive an order here to replenishment. And then you probably have a question. Here we already have no inventory. Why we are ordering here? For this red arrow at this time point, there must be another order coming in, which was placed one cycle time in the past. Okay, I will order here so that I can get here, or I will order here so that I can get here. Every time when I place an order, I expect it will be received very long later, and because of that, I need to place an order in advance. Okay, so with formula we have this. All we need to do is to adjust L into some other number that within 0 and T star. Okay, so we're going to use L to minus T star. If that's good, then if the result is within T star, then we can use that as our order to calculate our reorder point. Or if minus 1 is not enough, maybe we will minus 2, or maybe we will minus 3. For example, if R is so long, okay, then we're going to minus 2t, and then use this length to calculate our reorder points. So let's take an example. Suppose for IM airline, now the ordering lead time is 1 month. We know several information. The EOQ is here. The optimal cycle time is also here. The demand rate is something given. And the lead time here, 1 month, is roughly 0.083 years. Regarding reorder point, first we need to compare two things. We need to compare L with T star. T star now is around 0.289, and our L is just shorter than it, right? Or L is around 0.883. So if L is less than T star, we know R is just L times D. D is 500 per year, and our L is 1/12 years. Okay, so this is our reorder time, the reorder point. This point around 4167. This is the reorder point. When we see it, we place an order. What if the lead time is 4 months? Okay, in this case, the lead time is longer than the optimal cycle time, something like this. And in this case, we want to check whether L minus T star is less than T star. L minus T star is this place, okay, L minus T star, and it is within 1 cycle time. So we will try to place an order when we according to this time period. So the cycle time, the optimal reorder point will become 22 units, or around 22 units. Okay, so that's about positive positive ordering lead time. Now let's consider another situation. It's about economic production quantity. Now is that we are producing rather than purchasing products. So we will receive our products in batches. Okay, we are not going to receive all the products immediately at one single shot. We will receive, for example, 500 products today, another 500 products tomorrow, and another 500 products the day after tomorrow, and so on and so on. Even if we initiate a production process for 2,000 units, probably we need 4 days to receive all of them. Okay, this is different from purchasing something. When we purchase something, typically we get everything all together. So the inventory level will be something like this. Once we initiate a production process, we will have a few days for us to make production. So during this time, we will have an increasing inventory level. And then there will be another time with no production. During these days, the inventory will just go down as usual. One thing to keep in mind is while we are making production, we are also consuming products at the same time. Okay, so that's something we should keep in mind when we model this situation. In this new setting, we still want to find the optimal production lot size. A lot size just means the production quantity in each lot or in each lot. The optimal quantity will be called the economic production quantity, or EPQ. And then to model this, let's assume the products are produced at a constant rate of R units. Okay, each year we can produce R units. Given this information and all other information in EOQ, we want to find a lot size that minimizes the total cost. So again, suppose Q is our production lot size. We distinguish 2 periods. It's about uptime and downtime. Uptime means the inventory level is increasing, so this is the uptime. For downtime, that means the inventory level is decreasing, so here we have downtime. During the uptime, the inventory level increases at a rate R minus D. R is the production rate and D is the consumption rate. So the slope here is R minus D. Okay, and then the length of the uptime will be Q over R. Why? Here I'm saying that this length is Q over R. When we say we want to produce say 10,000 units, if each day we can produce 1,000, then the uptime, the production process will take 10 days to be finished. Okay, the total amount we want to produce divided by the production rate. So Q over R is this length. Okay, so the maximum inventory level that we may achieve at the end of an up period will be here. This is the slope, and this is the distance. Okay, so the highest point we will get is R minus D times Q over R. Still, the amount we produce will be depleted in Q over D years. Okay, I'm saying that this length is Q over D. At this time point, we initiate a production process for Q units, and that's for the consumption in this cycle time. Okay, throughout the cycle, the completion the consumption rate is capital D. So all the amount I produce will be finished, will be used out at Q over D year. Okay, so this is some information we know. Now we have completely characterized this figure. The key question is, what is the average inventory level? Okay, just like in the EOQ problem, we need to have the average inventory level. Here we also need an inventory level. So again, Given that these are all triangles, all we need to do is to cut it into half, right? And then R minus dQ over R divided by 2 will be the average inventory level. When we have our inventory levels going up and down and up and down like this, it's just like in average every day we have this amount in our warehouse. So the annual holding cost will now become this one. This is the average inventory level. H is the holding cost, unit holding cost. Annual setup cost. Now, capital K will be called the setup cost. It's the cost for we to initiate a production lot. Okay, it's equivalent to the previous ordering cost. The annual setup cost again is KD over Q, because this is the number of production lots we need to initiate. Finally, we want to find an a production lot size to minimize the total cost here. Of course, we can solve this problem directly because Q is here, Q is here. It's a nonlinear program, we know how to do it. But if we compare it with the EOQ model, this is the objective function of EOQ, we can see that the second term is the same. And for the first term, if we take Q over 2 outside, Q over 2 outside, then it's just that we are adjusting H to be H times 1 minus D over R. And we're going to call it an effective holding cost. Okay? That means all we need to do for solving this problem is to modify H into this one. Previously, when we have EOQ, inside the square root it is 2KD divided by H. And now it's just that that constant H becomes another constant, H times 1 minus D over R. One thing to keep in mind is D is the demand rate, R is the production rate. Of course, R is larger. Otherwise, it's impossible to satisfy all the demands. So if R is larger, this is going to make your holding cost smaller, right? It is H times something less than 1. If the denominator becomes smaller, then of course your Q star needs to become larger. And that's again reasonable because while you are producing, you are also consuming something. Compared with the previous EOQ case, when you produce, you get everything altogether. This will require you to produce slightly more. Okay, so let's complete our discussion with an example. Suppose now our department is not making airlines, we are making cars. So we need to produce 10,000 cars per year. Each car requires $2,000 to produce, and each run, each production run requires $200 to set up. Suppose the production rate is 25,000 cars per year. Let's assume the annual holding cost rate is 25%. This is saying that the annual holding cost is 2,000 times 25%. Okay. When we are saying about holding cost rate, that means we are multiplying that rate with the value or the cost of getting one product. Okay, the cost of getting one product is 2,000 and the rate is 25%. So then the product of them, $500, will be the holding cost per car per year, $500. Now the question is, what is the EPQ and the optimal cycle time? The EPQ again can be derived from this formula directly. It will be around 115 cars. The optimal cycle time can also be calculated. D over T star is the number of production lots we need in each year. Okay, so this is the number of lots, number of runs, and then 1 over that will give we the optimal cycle time, and it's around 4.21 days. Around 4 days we need to initiate a production run. there are some related questions that you will be able to handle by yourself. Will the annual holding cost and the setup cost still be identical? Or you may want to verify it by yourself. And then, what if there is a setup time? Well, just like we may have positive ordering lead time, if we have a positive setup time, so that we may start to produce products after that fixed time, when should we start to set up? Okay, that's some issue combining the two variants together. And finally, in each year, how much time is the uptime? We want to ask what's the ratio of uptime to downtime. Okay, some information that we may be interested in. And if you think about them, you will be able to handle them by yourself. Okay, so that's the end of our discussion about EOQ. In the next two videos, we will jump to another situation. Thank you.